Welcome to JRR Armory and our long-range shooting series. We're gonna look in part 2, vertical corrections, and basically answer the questions how fast we get to the target, and we will talk about density, altitude, and time to target. First, I like to cover the difference between accuracy versus precision. Accuracy is how close do we get to the target. So what is the average value compared to a reference value? While the precision is a measure of dispersion or standard deviation, if you will. So if you look at the different shooting elements, accuracy will tell us how close we are to the internet center of the target, while the precision talks about how widespread the group is. In general, spending more money on equipment will buy you potentially high precision through equipment, although the shooter plays an even more critical role in that, while a lot of the external ballistics will help us get higher accuracy, because if we do the right things, we will move the best group we can generate closer to the center of the target. I'd like to cover, however, some of the basic elements of ballistics. When the bullet leaves the muzzle, it does so with a certain muzzle velocity, and how we achieve that muzzle velocity is covered in internal ballistics, which is not part of this video. At any point in time, the bullet has a certain velocity and speed, which combined with its mass gives us the kinetic energy. This is covered by terminal ballistics when that kinetic energy hits the target. I will only briefly cover that. And one of the most important forces we are dealing with in this video is the drag, which is a function of air density, which is basically trying to slow down the bullet on its way to the target. The other major force is the gravity drop, which is an accelerating force. So when we are looking at long-range shooting, we have to account for that. Wind can also be a factor depending on the atmospheric conditions at the time. And finally, spin drift, because the bullets out of rifles are spin stabilized these days. That spinning creates a spin drift, similar, if you will, with a prop walk on a boat when you back for docking. The ballistic coefficient is a measure of how well the bullet cuts through the air, and each bullet, based on its design, has a certain ballistic coefficient. And if you'd like more details, there are also other resources online. You can go and check them out. They go into much more detail to cover that. External ballistics basically covers anything from when the bullet leaves the muzzle until the point it reaches the target. Very briefly on terminal ballistics and maximum effective range, I mentioned that the speed combined with the mass, the weight of the bullet, gives us the energy at any point in time. You can see at the bottom the 5.56 bullet, and at the top the 7.62. In general, 500 foot-pounds is a good number based on a small to medium target, not through hard barriers. So anything about 500, it's reasonably effective. So you can see that the 5.56 caliber reaching that point about 500 yards, and the 7.62 or 308 stays above 500 all the way up to 1,000 yards. So in general, depending on the type of your target and how much energy do you need to impact it, this can give you a high-level idea of the effectiveness of each caliber and the range for each bullet. If we go to the bigger boys, you can see that the 308 is the smallest on this picture. It has an effective range of about 800 yards based on this view. You can see 300 Winmag and 338 Lapua Magnum, around 1500 yards effective range. And the 50 BMG is actually a 2000 yards effective bullet or caliber. I mentioned gravity. It's a very important force we have to deal with. It's actually the law. So if you'd like to know more about it and see a very interesting Mythbusters episode, they have one where they compare the drop between a fired bullet and one bullet just dropped from the muzzle straight down. And essentially both bullets reach Earth at the same time, because the gravity starts to affect the bullet the instant it leaves the muzzle, and it's an accelerating force towards the center of the Earth. The accelerating constant, it's G equal 9.8 meter per second square, or 32.2 feet per second square. So at any point in time, the velocity of the bullet towards Earth equals G constant times time of flight up to that point, and the distance, it's half of G constant times the square power of time. So why is this important? It's because at any point in time, the distance traveled, which in our case becomes the drop, it's a square function of time. This is an example of a range card I'm using. We have covered it in part 1, the left side, which is a simplified chart to determine the distance in yards based on a mil reading. But if we focus on the right hand side, we see a table for the 308 Winchester, 168 grains, 2600 feet per second, 30 inch of mercury, 60 degree Fahrenheit, or so-called standard atmospheric conditions. The drop is listed in 50 yards, the distance is in 50 yard increments, correction in mils, time of flight, drop in inches up to 600 yards, and in feet afterwards. And you see the wind corrections in mils as well for a 10 miles per hour full value wind. If you remember, the function is a square function of time for the drop. So you see up to 600 yards, there is a certain linearity to the formula. From 6 to 9, it's a steeper drop, and from 900 and beyond, it's even steeper. And this helps us in having some rule of thumbs later on, that we can basically use straight lines in between these values and come up with some simplified functions. To understand the density amplitude and the corrections and the impacts between temperature and muzzle velocity, let's work through an example. We're engaging an 18-inch diameter, so 9-inch radius round target at a distance of 700 yards. If you look at the standard conditions, we should dial up 6.2 mils. The question is, are we going to hit the target? The answer is, it depends on the atmospheric conditions at the time and the density of the air that the bullet is gonna fly through, and the muzzle velocity compared to the standard velocity in our table. If we start with the density altitude, you will find several different charts like the ones I am showing here that will essentially show you that the density of the air goes down as you go up in elevation. It's almost a straight line function. So if we call 100% the density at sea level, by the time we reach 10,000 feet, we are only at 75% of that density. This is important because it means that the bullets fly easier through the air as we go up. Another important aspect is the ammo temperature muzzle velocity curve. As the ammo temperature goes up, and due to internal ballistics effects, that affects the muzzle velocity, which also goes up. So if the ammo is hotter, for example exposed to sun, compared to the standard temperature that we have listed in our table, then the speed will be higher. I like to simplify things, so for example in a 308 I'm using more of a straight line function. So we anchor the data in the lower table around 2600 feet per second for 60 degrees Fahrenheit. And then we go up in 30 feet per second increments for every 10 degree Fahrenheit. Then we go down in 15 feet per second steps as we go below 60. So this is an easy way to approximate if you don't know exactly what's the effect of temperature on muzzle velocity. If we do want to know exactly, we should use a ballistic chronograph. I recommend the magnetospeed in the lower right corner. It's a more modern, bit more expensive, but it's reliable and very accurate. And they have a sporter version too, which is also cheaper. So let's look at the density altitude. If we stay at sea level, the pressure of all the air above us, it's about 30 inches of mercury equivalent, column or mercury. And if we go, for example, at 5,000 feet, it's only 25 inches. So the rule of thumb is for every 1,000 feet we go up, the pressure will drop by 1 inch of mercury. The way to find out exactly what the density altitude is to use, for example, an instrument like Kestrel 4000, for example, which shows you the local atmospheric elements, temperature, density, altitude, pressure. However, if you don't have that, as long as you know the elevation and the rough temperature of the air, you might be able to estimate. Looking at the density altitude, I try to simplify it and round the normal charts you find on the internet. I have the elevation in 500 feet increments on the left side, the standard temperature for that particular altitude, and the pressure, the standard pressure for that elevation. And the simple rule of thumbs are for 1,000 feet, you drop by 1 inch of mercury, and you also drop 4 degrees Fahrenheit. And this works very well from 0 to 10,000 feet. Also, because the temperature is another factor in the actual density of the air, as you are deviating from the standard temperature at the given altitude, you can essentially add 1,000 of density altitude for every 15 degrees Fahrenheit above the standard temperature for that particular elevation. So let's look at an example. If we are at 3,000 feet and it's 80 degrees Fahrenheit, the equivalent density altitude is 5,000 feet. So it feels like we are at 5,000 feet, so basically the air feels thinner for the bullet. And this is because we are at that point off by 30 degrees Fahrenheit above the standard temperature. So it means we add 2,000 on top of the 3,000. Coming back to our example, are we going to hit the target? We now know that it's a hot day. It's an 80 degrees Fahrenheit, there is no wind, and we are at 3,000 feet elevation. So it feels actually like 5,000 feet for the bullet. The next adjustment that we need to look at is how the air temperature affects the muzzle velocity. And assuming we keep our ammo at air temperature of 80 degrees Fahrenheit and combine it with the table we discussed previously, this adds 60 feet per second to our muzzle velocity. So we'll use a conversion factor, and we are going to turn that also into a density altitude equivalent based on the temperature. I haven't seen this done anywhere else exactly the same, but I think it's a nice and simple method. So we basically end with one number density altitude correction factor, which includes also the change to muzzle velocity due to temperature. So in our example, the formula you can see in the lower side of the table, we need to add 1000 to the density altitude. So a change in 60 feet per second, it's equivalent to being higher up by another 1000 feet. So we start with the 5000 from before plus 1000 equal total density, air density equivalent of 6000. So I need to correct the drop by 6 times 0.09. This uses the last portion of our chart. So for every 1000 feet of equivalent density altitude, there is a certain correction factor. For the 700 yards, this is 0.09. So 0.09 times 6 equals rounded 0.5 mils. If we wouldn't have made the correction, we would have missed high by approximately 0.5 mils or about 12 inches at 700 yards. And if you remember, our target was 9 inch in radius, so this would have been a miss above the target. The card here summarizes many of the concepts we have addressed. The ammo temperature to muzzle velocity effect. The fact that if the pressure goes down, the impact goes up. Humidity we haven't mentioned yet, but essentially it can be ignored. It has a very negligible impact. You can use 50%. Also, the changes are for every 1 inch of mercury or 1000 feet, and the temperature drops by 4 Fahrenheit for every 1000 feet. Another rule of thumb is that for every 1 degree Fahrenheit up from standard, the muzzle velocity goes up by 3 feet per second, and for every 1 Fahrenheit down, the muzzle velocity drops by 1.5 feet per second. Another rough way to do it is for every 20 degrees Fahrenheit, make a correction of 0.1 mils per 100 yards. We'll show an example of how that works, but it's not something we recommend. And finally, at the bottom of the table, you can see that the impact of a change of 1 inch of mercury, 4,000 feet in elevation, or a change of 20 degrees Fahrenheit in ambient temperature, or a change of 30 feet per second for muzzle velocity, each one of these has an impact of 0.1 mils for 700 yards. So our second method, which is still okay to use, we are in the same day with 80 degrees Fahrenheit at 3000 feet elevation. So we have to correct by 3 inches of mercury, so it's a plus 0.3. We know it's 80 degrees versus 60 degrees, so we add another 0.1. And we know finally that the muzzle velocity goes up 60 feet per second, so we add another 0.2. So the total correction with this method, with the second best method, is 0.6 mils. So you'd have to we have to dial 6.2 plus 0.6 equals minus 5.6. With this method, we are hitting slightly lower, but in the zone, all else being equal. The third rough method, which is pretty rough, it says that for every 20 degrees Fahrenheit, we will correct 0.1 for 100 yards. So 0.1 times 7 gives us a correction of 0.7 mil. So we would have to dial minus 5.5 mils, so it's still lower, but still in the target zone. So if we are to plot the hits or misses, if we wouldn't correct at all for temperature or density altitude, we would have missed high. And the first method from the previous page puts us closest to the target. Next one is second best, is the second method on the left. And then the third method is the least accurate. However, all three methods in the end are better than making node corrections for density, altitude and temperature and muzzle velocity. By now you probably know that I'm a big fan of analog tools in the field, slide ruler. And this is another interesting tool I found called Field LCT Altitude Compensator. It essentially achieves some of the same goals that we have described previously. So please look into that, and if you are interested in it, possibly place an order for that as well. I think it's always good to have a type of analog tool in the field, because all electronics sooner or later fail on us. I recommend, for a more in-depth view, to look into the work of Brian Leeds. He's a ballistician for Burger Bullets, and he has some excellent applications and software. Or for an in-depth look in all the things related to long-range shooting, you can check out the Sniper 1-on-1 series by Tiborosaurus Rex, which you can find here on YouTube. It's an excellent resource for long-range shooting, extremely detailed. So we are at the end of part 2, which cover how fast do we get to the target and what type of vertical corrections we need to make. And please stay tuned for part 3, where we will look at how straight do we aim and what type of horizontal corrections are needed based on the wind or moving targets. Thank you for watching. Please stay safe and comment, subscribe and share.